Hello and welcome to the last lecture of this semester about machine learning operations. This lecture will be about ML antipatterns. So let us briefly resume what is an antipattern. You know the concept of an antipattern or of a pattern from software engineering. Basically, an antipattern is something that we do, either a process, a structure, or a set of actions that were initially thought that they will be useful, appropriate, effective as a response to a problem, but unfortunately these actions, these patterns, they have unforeseen consequences which usually bring more harm than good. Sometimes anti-patterns can be the result of addressing a problem without thinking about long-term consequences, something that you've already seen in the terms of the technical debt. The difference is that a technical debt is neither good or wrong, as we've discussed it at length. A technical debt is simply something that you will have to pay as a consequence of the decisions you made today further down the line. Now, anti-pattern is different from the technical debt in that it is basically a shortcut. You do something in a short term to solve the problem without thinking about the long-term implications or without thinking about the larger context of the entire software system. The anti-patterns can emerge at all levels of the system, so at the design level, at the architectural level, at the code level, and even after the code has been written in the testing. So, for instance, recalling some well-known anti-patterns from software engineering, at the design stage you could, for instance, find the anti-pattern of the God class. The God class is a situation where you have one single class which has almost all of the responsibilities. It's just a huge class with very complex interface. A feature envy anti-pattern is a situation where one class is extensively using the interface of another class, right? Asking for or sending communications and executing methods and functions of another class, which might mean that the responsibilities are wrongly divided between the classes. At the architectural level, anti-patterns usually address scalability, flexibility, or reusability. So, for instance, a big ball of mud is a common term for the anti-pattern where you have no clear distinctions between modules. You don't have a nice demarcation of responsibilities and so on. In microservice anti-patterns, it could mean, for instance, that you design too many microservices, or that microservices are so tightly coupled that they behave like a single one system, which basically defies the purpose of the microservice architecture. Blob architecture is another word for a God class, basically raised at the level of the entire architecture, where again you see one huge module without the distinction, without modularity that allows for scalability and flexibility. At the code, of course, there are numerous anti-patterns that refer to the code. Some of the anti-patterns that I named here, the magic numbers, is of course the anti-pattern where some numbers are hard-coded into the code base without proper justification, without the ability of changing the numbers, without the need of recompiling the entire software. You can have a duplicate code. This is a very popular anti-pattern where exactly the same or very similar piece of code is repeated across classes, or spaghetti code basically. It's a moniker for a badly written code with a lot of complexity. And finally, at the testing, if you don't write enough tests, unit tests, functional tests, integrational tests, that means, of course, that you can miss bugs, you can have additional costs in development. And the anti-patterns here are, for instance, stub testing, where instead of testing the real class, you quickly build a stub, which is a super simplified version of the class, and you test on the stub instead of the original class. You can have a blind testing. This refers to the situation where testers write the code without proper knowledge and understanding of the full complexity of the system, or smoke testing, which is basically when you write the codes when you write tests just to have them. It's like a smoke screen, right? There is a test coverage, but the tests are so simple and so basic that they don't even count. So why do anti-patterns emerge? Sometimes they emerge just because people are bad coders, sometimes because people are lazy, sometimes because people are under pressure and they have tight deadlines. There are some expectations which might be unrealistic about the speed and the scope of the system which is being developed, and this compromises the health of the software in the long term. Of course, the anti-patterns quite often result from simple lack of knowledge and competences, right? People don't have the knowledge, don't have the understanding, they don't know what are the good practices, people just blindly copy-paste solutions from Stack Overflow and so on and so forth. In the case of large systems, especially when you have a large software system and the machine learning is just a part of it, there could be some anti-patterns emerging because of the communication breakdowns, where different parts of the team do not communicate properly, and there are different perspectives between subject matter experts, testers, business owners, product owners, machine learning researchers, machine learning engineers, and so on and so forth. And finally, documentation. Writing documentation is becoming much easier now with the help of LLMs and other code assistants, but still the absence of good, high-quality documentation can lead to repeating mistakes that appear in the code base. As you know, machine learning is fully data-driven, and most of the anti-patterns we'll be discussing throughout this lecture refer to wrong data handling. And these anti-patterns represent simply errors made throughout data pipelines and data monitoring practices, or to be more precise, the lack of good data monitoring practices. Of course, there are also specific anti-patterns related to ML at the continuous integration and delivery. So at all stages that we've discussed throughout this series of lectures, to remind you, we've discussed what happens before the production, so design and development. Then we've discussed the MLOps at production, so performance evaluation, and after deploying to production, which is deployment and maintenance. And this, of course, again, goes back to the idea of the technical debt, something that we've discussed, and here I will send you back to the slides that are available at the course. So let us now go through anti-patterns that are ML specific and that we'll be discussing throughout this lecture. The first one is data leakage. The general idea of the anti-pattern is that the model is making use of data that it is not supposed to have access to. Right? So usually it's the problem of the demarcation of data between the training and testing and inference. Or sometimes the data leakage is about the mishmash of data at the training and inference time. So, for instance, something called a peekaboo, which is basically looking into the future where you're not supposed to. Imagine a time series data set. You have a data set that represents some events, some actions on the data, but the data set reporting, so the actual label, the ground truth that we associate with a given data item, may lag the actual measurement, the thing that we've recorded in the data set. So if we have the availability of the data lagging behind the availability or the date of the measurement of the data, that's when a peekaboo can happen. So the model during the training can have access to the measurements for which the action, the ground truth, will be reported later. The temporal leakage. This is far more frequent than you might think. If we're doing train test split on the data which has a very strong time correlation, then of course by splitting on time we are introducing a very high correlation or temporal dependence between the train and test, which may of course invalidate all the evaluation of our models. Sometimes it's just temporal dependence, but that may even go further into the domain of causality, right? When previous data are causally related to further data. And of course, in time-related data, we always want to divide the train and test by time, right? In order not to introduce this peekaboo, if we were to divide randomly between train and test. But unfortunately, we also have to think about the temporal dependence and causality introduced by time. The oversampling leakage. This is something really hard to notice, and it's a very common error. So imagine a situation where you have a highly imbalanced data set, and in order to improve your model, you decide to do oversampling. And there are many methods for oversampling, but you decide to do the minority class oversampling before the train test split. And that is an error. Why? Think about popular oversampling methods, for instance, the SMOTE method, where you create artificial synthetic data items, the oversampled elements by, for instance, averaging information from existing real-world data. Then these oversampled synthetic data, they carry on some information about real data. And if you then divide between the train and test, and you put these synthetic data into the training, you allow for the leakage between the train and test, so the data from the testing, which are in theory the data that the model did not have access to during training. In fact, the information is being leaked due to the oversampling method. And this oversampling method usually creates these synthetical data sets or synthetical data items by some kind of averaging of real-world data. And the fourth example of data leakage anti-pattern is metrics from beyond. This is again very hard to notice and to protect against. So imagine that you do some kind of pre-processing before again train test split. For instance, you do standardization, right? You turn the numerical variable into standard numerical variable with the mean of 0 and standard deviation of 1, or you do some kind of normalization or whatever. Then if you do this before you start dividing data between train and test, you don't leak actual values, but you leak variance and standard deviations, right? This is also some kind of a data leakage, information leakage in the training pipeline. So here is again the oversampling leakage illustrated in the image. You can see that if you do this in the wrong way, depicted on the left-hand side, you have a data set with a minority class. You oversample the minority class, so now you have a balanced data set, and now you divide. First of all, the test set is not representative of the original data set because you have the data oversampled, and also the information from the synthetical data is being put into the test set or into the train test, which is wrong. The correct way is to first divide between train test and test and between the train set and the test set, and after that you oversample but only on the train set. Right? So the model can learn something from the minority class. It is not overwhelmed by the majority class, but when you evaluate on the test set, you evaluate it in the conditions that are representative of the target environment in which the model will be deployed. Another anti-pattern is called act now, reflect never. Basically, this is when you believe that your job ends at deploying the model in production. So you design the model, you train the model, you might even measure the model and evaluate it on different metrics, and then when you're satisfied with the metrics, you just put the model into production and you use it as it is, without any filtering, without any guardrails, without any reflection on the model responses, without even periodic manual inspection. This, of course, leads to all kinds of dangers. First of all, remember that most production environments are hostile. There are agents that are actively acting against the machine learning models, that are trying to poison the models. Even at the inference time, they are trying to break the models. And if, for instance, as expected or as suspected, rather, I should say, some companies are using the inference data, especially the queries, to further train the data. This is, of course, the open avenue for model poisoning. So what we're supposed to do here is, of course, we should introduce some systemic approach to monitoring, to tracking, and debugging of deployed models. We should always watch for a situation where model predictions begin to deteriorate, so we should always evaluate the model predictions also in terms of their trustworthiness and trying to detect the attacks, the adversarial attacks and poisoning of the model. There are some tools that you can use here, for instance, using the ML explainability framework, such as, for instance, the LIME framework could be useful if you evaluate the model responses via LIME and you suddenly see the shift in model explanations where different variables begin to play an important role in predictions. This might be, for instance, the sign that something is wrong. There is also an approach, a very general approach called fusion and suppression metamodel. This is a framework in which you first do the fusion stage, where either multiple modalities are joined into a single representation. So you take different modalities, text, video, images, and you try to build a single combined representation in some embedding space for the model training, assuming that this will lead to better predictions. But then you go into suppression phase, in which you are actively trying to filter out features or parts of the representation which are not relevant. This fusion might be at the level of features, but it could also be at the level of models. So you can have several models working in tandem, where you ask many models at the same time, and the suppression, for instance, introduces some kind of a weighting for model responses, so that you take into consideration only the most relevant models. You see this, for instance, in LLMs, in specific models which are very successful, such as Mistral or the recent DeepSeek R1, which use the mixture of experts, where you have smaller LLMs, highly focused on specific either data modalities or problem sets, and then you have the gating model, which defines or decides which experts are relevant for the given query, and then this model creates a single response by weighting and filtering out parts of the responses. So this also, the mixture of experts, could be regarded as a implementation of this more general fusion and suppression metamodel. Another one of anti-patterns is tuning under the carpet. This is the situation which is again quite common, unfortunately, where when working on the model, you try haphazardly to optimize the model, especially optimize the hyperparameters, and if you don't document your path, and you just come up with a single model saying, hey, look what I found, these are the best values that I was able to find. This, of course, hinders the reproducibility of the model and the adaptability of the model as well. You're supposed to know what is the effect of hyperparameters on your model, on the performance of your model. If you have a model which is really bad across the hyperparameter space and only for a very, very specific set of hyperparameters it performs well, that does not bode well for the future of the model, because the model will deteriorate, there will be concept drift, there will be data drift, there will be feature drift, so the model will fall from this nice small area of fine-tuned hyperparameters and will drop the performance. It really doesn't matter whether you do manual tuning or grid search, whether you do some random search, or you use some meta-heuristics like simulated annealing or tabu search, or you use some kind of Bayesian optimization. You are supposed to document this entire hyperparameter optimization pipeline. It should be reproducible. You can use additional tools. For instance, you may use the notion of Shapley values to attribute importance to specific hyperparameters when looking at the importance for the objective value. Right? There are ready-to-use libraries that allow you to, for instance, compute which hyperparameters have the biggest impact on the value of the objective function, and then by tuning these hyperparameters you can see if you are in the stable area of the hyperparameter space or not. Next one, perceived empirical superiority. This is an anti-pattern which boils down to wrong evaluation of ML models. Sometimes people just use their intuition, they use shortcuts in empirical evaluation, they just do a few tests. Sometimes they will use wrong baseline, sometimes they will say, well, this is the state of art. Sometimes they will use arguments such as everybody knows that X and Y and Z without sufficient and proper empirical evaluation. So what are the results? So for instance, in terms of reinforcement learning, there are many documented cases where metrics or variability of results completely lack statistical significance. So people attribute the success to something, right, in the training process or in the model architecture, where in fact, for instance, the problem may be obvious, or there might be some huge flaws in the data training that allow the model, for instance, to go and find a shortcut and like, for instance, the label leakage between the training and testing. Sometimes the problem will not, this anti-pattern will not allow you to find a really good solution. Consider the fact that most people today will tell you just use transformers. Transformers are so much better than any other model, so don't bother even looking at older architectures because it makes no sense. Which is not true, because there are again very specific tasks where if you just stack a couple of LSTMs, you will get much better results than you get with transformers. Just transformers are not that universal as you might think. People engage in Bayesian deep learning because it's cool, because it's a nice math, because they learn something and it brings some kind of unique capabilities and unique competences. But if you do the Monte Carlo dropout long enough and you allow it to run to completion, you will get the better results than trying to train Bayesian deep learning. And finally, people are so accustomed to contextual embeddings that they will not even try to use older static embeddings. And static embeddings are simple, are faster, are much cheaper at inference, and truth be told, they might be much better because they can be easily fine-tuned for a specific use case if you need a very, very specific case. So if you just believe that static word embeddings are a thing of the past, that might prevent you from finding a good and cost-effective solution. But credit assignment, again, another anti-pattern. Here the problem lies in incorrectly identifying what causes the performance gains or performance losses in the modeling pipeline. So you might find people who claim that stacking another level, another layer, changing from one activation function to another, fine-tuning of hyperparameters, using some complex learning rate schedulers, and so on and so forth, that these are the reasons for performance gains, where in fact it's basically, for instance, the wrong baseline, or something in the data pre-processing that has changed, or a very, very simple hyperparameter tuning, or for instance, the failure to properly formulate the problem, right? And trying to solve, for instance, a much simpler problem than the original problem. So how do we prevent this anti-pattern? Probably the best thing to do is ablation studies. You will see ablation studies in every solid paper that presents a new model. And if you look at the ablation studies, in a very simple terms, even simplistic terms, you may think of it as given many dimensions on which model can be changed. Think hyperparameters, think data processing pipelines, different data regimes, different amounts of data for training, and so on and so forth. So you have several dimensions on which you can put your training pipeline. In ablation studies, you freeze all but one, and you just change one parameter and having everything else frozen, right? So for a given set of all hyperparameters, let's see what happens if we increase the size of the training data set. Let's train the model on 10,000 elements, 50,000 elements, 1 million elements, 20 million elements, right? And let's see if the data, if the model gets better at the high data volume regime, for instance, right? Or we could say, let's see what happens if we limit the amount of available memory for the model. So we have to quantize the model, or somehow simplify or even binarize the model, or something like that. So yeah, this is basically the ablation studies will be the simplest solution to this problem. Grade your own exam. Well, grade your own exam, it's rather a cultural thing. It's an anti-pattern that pertains to the organization rather than the pipeline itself. So if you have a data science team that is responsible for everything, for training, for testing and evaluating, the team might build a false confidence in the results and not spot the problematic elements. So people might not think about validating the results or finding really competitive baselines or running against other methods, especially simple methods, right? People are so much attached to neural networks that they will not consider SVMs or simple Bayesian classifiers. When, in fact, for instance, for a given problem, the problem is so simple that naive Bayes classifier is on par with a trained neural network. What to do to prevent this anti-pattern from happening? Basically, make sure that the testing and evaluation is done independently. The best thing you can do is, of course, have different sets of people with different perspectives and with different expectations and with different different skills and yeah, basically perspectives on the data set. And of course, always guard the evaluation data set only for the final evaluation. Never allow to test the data on this final evaluation and then retrain the model, because then you will lose the ability to do anything reasonable and to have really strong evaluation of the model. HARKing. HARKing, this is an acronym that stands for hypothesizing after the results are known. This is an anti-pattern that is most commonly found among ML researchers when, after building the model, after fitting the data to some kind of a function, we retroactively try to formulate a hypothesis that we then prove with the model, right? So this is a very serious experimental design flaw. You always have to have a hypothesis before the experiment, not after, right? You design the experiment for a given hypothesis, not construct a hypothesis for a specific outcome, right? Because post hoc you can basically hypothesize anything, and mostly these hypotheses will make very little sense. So after you observe the outcomes, it is strictly incorrect to do post hoc hypothesis for observed outcomes. You always start with a hypothesis and then you observe outcomes, and these outcomes either confirm or reject the hypothesis, not the other way around. In data analysis, this HARKing might take different forms. It could be cherry picking of data, so let's take only the data. Let's use only the clean data for our model, right? Let's throw away data items that have more than 10% of null values because they are obviously wrong, and when it comes to real-world inference, you'll find that most data sets will have more than that of null values. It could be p-value hacking. P-value hacking refers to the situation where you set some kind of a confidence, statistical confidence level. You set this p-value, and then you make multiple experiments with different, with changing maybe hyperparameters, train test splits, data regimes, pre-processing techniques, and so on and so forth. So you are making multiple attempts to cross a given p-value, right? If you do multiple experimentation, there are well-known corrections that you do to the p-value to account for your multiple experiments, right? Usually it's the Bonferroni correction of p-values. And HARKing usually, I'm saying that this is mostly ML research thing because it applies often to training of models for the sake of publication. Because the science and scientific world has a well-known positive bias for good results, for positive results. Publishing of negative results is hard. Journals are not interested in papers that state we've tried X and Y and Z and unfortunately nothing worked, right? You really struggle with publishing negative results, despite the fact that if you think about the science, almost every result is negative, right? It must be, otherwise we would already have hovering roller skates, and we don't have those. So yeah, almost everything doesn't work in science, and people are strongly incentivized to report positive results. So people overstate the results. They usually hide the contradictory findings, they downplay the negative results, they report partially the results, only the results that agree with the hypothesis, and the hypothesis is quite often formulated post hoc, so we just or just report on what aligns with pre-existing beliefs and expectations. This is all, of course, wrong. This is a strong anti-pattern, but it's really ingrained in the current scientific world. Okay, the next one, set and forget. Set and forget, also known as phantom menace, is basically the idea that the model will work on the data which is independent and identically distributed to the data on which the model has been trained. Right? The IID hypothesis states that, of course, the data generating process produces the IID samples, and people assume that you can train and then you test, and at inference in the future you will be working with exactly the same data, which is not true. Because if you have this set and forget mentality, that means that you are not thinking about the future. You're not considering the fact that in the real world there will be concept drift. There's nothing you can do to prevent it. The world changes constantly, and the data changes, and the data distribution that generates the data changes, so the queries will change, the predictions will change, the feature distributions will change. You have to notice the model change, you have to monitor the model, you have to measure to which extent the model is still a good representation of the reality. And there are several methods to do this. You can, for instance, build simple rule sets for predictions, just to notice when the new rules are appearing, to notice the model change. You can have, as we've discussed previously, you can train the classifier that tries to discover if a data item comes from the training data set or the inference data set, and when the model, you expect that this model will have a terrible accuracy, because there is nothing in theory that allows you to tell apart train instance from the inference instance. And the moment the model becomes better, the moment the model picks up on some features that allow you to distinguish between the training and inference, that means the change is big enough and you're supposed to retrain the model and enter again this feedback loop. You could change the evaluation procedure. For instance, a simple solution is to have a sliding window that goes over all instances, and it weights the instances by diminishing the weights of older instances. So when computing the evaluation scores, the metrics that you use to monitor the model, you may put more weight into the more recent instances, and then, of course, if your model starts to deteriorate, you don't see the positive impact of old instances when the model was still a good representation of reality. Instead, you see a gradual decrease in the metrics because the model is struggling with more recent elements. And there can be additional methods, especially in the world of Bayesian modeling. There are some methods for concept drift discovery. A concept drift discovery is, of course, the situation where you see the change in the distribution of the label. So I can send you also to these solutions. Communicate with ambivalence. This anti-pattern refers to the fact that usually the models just produce predictions and sometimes produce also the probability of the prediction, but very, very few models are able to also clearly communicate the uncertainty of the prediction. And this is something that people just take for granted. They don't think about it, but in the different parts of the data manifold, the model might have lesser or greater uncertainty about the prediction or its evaluation of probability. And a simple solution is to use the Brier score. Here again, I will send you to, or I will put the link to the description of the Brier score. It's a very, very simple measure that allows you to compute the performance across different models. It's a strictly proper score function. It's a very, very simple formulation. You just take the average square difference between the probability, the predicted probability, and the actual outcome, and this gives you an unbiased estimator for the quality and uncertainty of your model, right? So a metric which is not very popular, not widely known, but very, very strong and very, very useful. So I will urge you to look at the Brier score and use it in practice. Data crisis. So this anti-pattern is specific to complex data sets in which you're supposed to perform some kind of manual modification of the data. If your data is extracted manually from some hard sources, right? Sources which do not give you a nice clean interface for reading. This could be some legacy data storages, it could be some strange data formats. These can be the data that really require manual processing, manual sanitization, for instance. If the part of the data pipeline involves the personal information removal, right, the sanitization about PII, then this anti-pattern might appear if you have this data, let's call them sensitive data, sanitized by some data steward. Usually it's done simply manually. If it's not the part of the proper data processing pipeline, these data preparation steps will be very, very hard to reconstruct and repeat in the future. Again, here it's more of a data engineering problem. So if you have good data engineers in the team, make them set up good data engineering practices, clear pipelines, well documented, with all the data provenance information, the origin of the data, who is the steward of the data, who touched the data, how, what was done to the data. So build data pipelines that are governed, that are documented, that are resilient, that are flexible, and that can be repeated in the future. Solutions such as feature stores help a little bit in this regard. Modern database architectures like data lakes or data mesh, especially a data mesh is a new concept in data engineering, where you think of the data items as products with everything around them. So it's also a nice perspective to think about the data for machine learning. Write data tests, not only code tests for code coverage. We've discussed at length the need to write data tests. And you have libraries that allow you to write these by assertions, by writing the functions that evaluate the data quality, and track the data, make sure that you have all the data provenance, you have the data pedigree, so where the data comes from, who is the owner, what is the lineage, how the data relate to each other, which processing pipelines transform the data. It's a whole world in itself, right? That's why good data engineers are gold. Right? This is really hard. This I don't think it will be easily automated in the near future. So think seriously about data engineering in practical machine learning. Now let's finalize with data glazing. This is a new concept. This is something you should be aware of, and it's super interesting. So it applies specifically to generative AI. As you know, most models, be it language models or vision models, are trained on the data that has been stolen from the internet. The companies that are responsible for training the models, they didn't ask for any consent. They just took everything scrapped from the web without knowledge of creators, of artists, without any credit, without any consent, without any compensation, which is basically stealing, right? And as long as you're not, as long as it doesn't concern you, you might not think about it as a social problem, but it is a social problem, and it is a very big problem. So a lot of these models apply style mimicry. So you can ask the model to generate images in a given style, in the style of an artist, a painter, a photograph, visual artist, a musical artist, or even a writer, a poet, whatever. And the models, especially the models which are fine-tuned, and you can cheaply fine-tune models using low-rank adaptation, they produce images or musical pieces or texts which are in the style of the target artist. Now, why I'm claiming that that it incurs a significant societal cost? Over 1 year after the deployment of Stable Diffusion and the DALL-E, in the Netherlands, the market for small form visual products. Think about, posters, design graphics for menus, for little things, cartoons, leaflets, and so on and so forth. 95% of the market disappeared within 1 year. So put yourselves in the shoes of someone who is trained as a graphic designer when someone steals all your work and then puts you out on the streets without any means for living, right? It hit hard, especially the young artists, without any commissions, without basic income, the loss of reputation, of course, because these copies might be of very, very low quality. One artist even complained that the first 10 hits in Google, when asked about her works, presented Gen AI works in her style that were not altered by her. So not only stealing the commissions and basic income, but even stealing the artistic identity of a universe. So what is data glazing? Data glazing is a very, very interesting way to fight large corporations which steal the data for model training. The general idea is to distort the images, but distort them in such a way that human eye do not perceive the distortion. But the distortion very, very significantly shifts the elements in the embedding space in which the models produce the images. So, as an example, consider the Alice in Wonderland. Right? The original graphics, unfortunately, out of the blue, I don't remember the name of the author, of the artist, but these images are very, very specific, right? So the model, I believe it was Stable Diffusion, fine-tuned on the images of the author of illustrations for Alice for Wonderland, produced the images that you see here. And as you can see, these images, right, the style mimicry, generate the image of the dog in the style of, and here is the name of the author, produce something like that, which is quite similar to the original style, right? And you can imagine this applied to any artist you can imagine. Now, here are exactly the same images produced on the glazed images. Right? You can see that the style is completely different. So how do the glazing works? So you might go for a very, very simple solution which doesn't work. The simple protection from these practices of stealing the data is to dirty label the data. So idea is the following, because of course all these models work exactly the same way. They scrap the internet, they scrap all the pages, the images, and they look for image captions, and of course then they compute the common embedding of text and images. if you are able to poison the training data set by providing purposefully wrong label, right? So you claim that this is the image of the dog, animal, dog, pencil drawing, dog, digital art, and so on and so forth. Then the model might learn that this is a dog, and every time someone asks, generate the image of the dog, right, the model will in fact produce the cat. What is the problem here? The problem is that humans are very good at spotting this. And these companies are well known to use slave labor in third world countries, so it's absolutely not a problem to hire a couple of people in underdeveloped countries and ask them, put them for 20 hours in front of the screen and tell them, please sanitize this training set by computing, by checking if the labels are correct, right? So this can be done very, very easily. So this is not the way to fight this phenomenon. Now, the glazing, and one perfect example of glazing is a library called Nightshade. What it does is basically you have to define what is the anchor image to which you want to glaze your original image, right? To poison the image. So you have the image of a dog. It has a label, a photo of the dog, and the label is aligned with the image. That's right. Then you select an anchor image or anchor concept. So for a dog, you select cat, and then you compute the minimum distortion of the pixels here that in the feature space will move the representation of this image toward the representation of this image. So when the model computes and generates anything related to the label dog, in fact, it will use the images which are in the feature space close to this image. So basically, these will be the images of cats. And the same is here. So a dog portrait, you take this image, you find the anchor image, and you compute the minimum number of pixel changes to this image that will shift the representation of this image towards the representation of this image. That's how the Nightshade works. Now you might ask, okay, if I have to change pixels from here to here so that the embedding of this image is very close to the embedding of this image, this will surely ruin the original image. Now, the beauty is that it does not. So here you have the original image, and this is a poisoned image. This image, when embedded by Stable Diffusion, will point to a completely different part of the data representation than the painting of the dog. Also, the Stable Diffusion doesn't see a photo of a BMW car here. What the Stable Diffusion sees here is a cow. Now, this image has been poisoned, turning this car into a cow. Here we have some fantasy art painting or the original work of art. Basically, the idea is that it's unperceptible, people cannot perceive the difference, right? There's no way you could look at the image and say, oh, this one has been changed, right? No way to do this. So if you manage to poison the model training with enough images that were shifted in the feature space, then of course the model breaks down and is unable to produce any reasonable results. So how many images do we need to poison a large Stable Diffusion model? Again, the beauty is that we need just a few. So here is the example from the original paper presenting the Nightshade Poison Pill. This is a clean model. This is Stable Diffusion, the large one, the extra large one. So it's really the big model that people are using for generative vision and to steal and produce the images in the styles of certain artists' styles and so on. Here is the concept that is being poisoned. Here is the concept to which a given concept is being poisoned. So all dogs will be poisoned toward cats. Cars will be poisoned toward cows, handbags to toasters, hat to cake, and so on and so forth. Right? So, in the whole image net, which consists of 1 million images, if you manage somehow to inject 50 poisoned samples of dogs nightshaded towards the cat, this is what you will get every time you're trying to generate anything about the dog. If you manage to put 100 poisoned samples, this is what you get every time you ask for a dog. Paint me the image of a dog riding a motorcycle. Every time you'll get this one. For 300 poisoned images, this is what you'll get. And the same with a car. So just 50 poisoned samples already prevents you from generating any cars. But the more you get, the closer you get to cows. And the same for either the styles, so from concept art to abstract, from cartoonish to impressionism, from cubism to anime. You can do this whatever way you want. And the beauty is that here the economy is working, is supporting the artists, basically. Because the costs of fine-tuning and training the model are so huge that if people start nightshading the images on the internet, and let me remind you, there is no way you could easily tell a nightshaded image from original image, that the risk of ruining your entire training, because there is no way to unlearn the data that you have already put into training, the sunken cost of training is much bigger than just using the collections of images that the artists allow to use with proper attribution, with proper compensation, with proper licensing, and so on and so forth. This is just the beginning. Not only the models can run out of the data, they can run out of good data for training. And if you don't think about the source of the data, you might quite easily get into the trouble of using poisoned data samples. The same can be done for audio, the same can be done with video, and hopefully the same will be done with text, so that large language models will not be able to do style mimicry. And finally, the last issue I want to mention during this lecture is the problem of complex evaluations and interventions. So think about ML model and think about the way you usually evaluate the model. You select a couple of metrics, right? You take the precision, recall, the F1 score, maybe sensitivity, accuracy, micro-weighted, and so on and so forth. And you just compute a bunch of numbers, and that's it, right? And then you say, oh, here is the confusion matrix, here is the receiver operator characteristics, here is the best point, and so on, maybe a lift curve, whatever. The problem is that real-world systems, the production systems, they work differently. They consume the result of the ML model, but the result, the prediction, is used downstream. And it can be used in two ways. It can produce a notification, so the process can consume the result of an ML model and then produce a notification, right? Send an email to the user. We think that we've stopped your transaction because we think it is you are under a phishing attack, for instance. Or a process consuming the result of the ML model could produce an intervention. So there is some kind of an action being done, right, as a result of the notification system. And you should think of an ML model in the scope of notifications and interventions. Let me clarify this by a specific example. So think about transaction processing. There are transactions in some financial institutions. There's a bank, there's a new transaction, and we have to spot the suspicious transactions, right? So there are two results. The transaction is favorable or unfavorable. Favorable means that transaction is absolutely legit, everything is okay, the bank should proceed with the payment. Unfavorable means that we should stop the transaction because we are protecting the user from financial loss. And the model just gives you the prediction. It predicts that either the transaction is okay or that the transaction is suspicious. And based on that, of course, then we compute whether the model was wrong or not. So if the model said the transaction is unfavorable, means suspicious, and it was really a wrong transaction, right? Someone was trying to steal from us. This is a true positive. Let's assume that the positive class means spotting the suspicious transactions, right? We can have a false negative, false positive, and true negative. So that's all and clear. This is in theory. You know this saying, right? In theory, there is no difference between theory and practice. In practice, there is. So in practice, we'll have transactions. If the model says the transaction is favorable, then nothing happens. The system proceeds, right? The money goes out of your account and you pay for something. But after the system detects a suspicious transaction, then we have two options. We can either notify the user or not notify the user. If we don't notify the user, there will be some sub-process after that dealing with the transaction. If we decide, if we decide that we send a notification, as a result of the notification, there could be an intervention. Or there can be lack of the intervention. We can ask the user, please do something, and the user intervenes. Either intervenes or does not intervene. So let's take as a very specific example. So we have a transaction. The model says transaction is okay, it's favorable, it was really favorable. Yeah, great. True, negative. This is like 99.9% of all transactions. Unfortunately, if we say everything was okay and the transaction was bad, then this is the big problem, right? We allowed our client to be scammed, to be robbed. Now let's take a look at this part because from the practical point of view, this is much more interesting. So the model predicts that the transaction is suspicious, and we decide not to go with the notification. We don't notify the user. It turns out that the transaction was okay. It was just some atypical transaction for a customer. Right? This customer has never withdrawn 1,000 euros on Saturday morning, but this time she did. Right? So basically the result is, yeah, sure, perfectly. I didn't rely. It's good that we didn't rely on the ML algorithm because the transaction was correct, despite the fact that the transaction was predicted as unfavorable. Now, this is really bad, right? We've decided that the model said it's a suspicious transaction. We decided not to take any action, and yeah, we could have informed the client, but we didn't. Then we send a notification, and with the notification, the client decides not to do any intervention. So we send the notification, but everything was okay. So this is basically the boy who cried wolf. If the transaction was wrong, then of course the bank says, well, I'm not really happy. We sent you the notification that something is wrong, but you did not respond. You didn't do anything. So we were right, but unfortunately you should have intervened. So you were at the loss. And if someone intervenes, there are two more outcomes. So as you can see, in practice, it's really not, it doesn't stop at the prediction, right? The model, you were responsible for developing and deploying the model. The model gives the predictions, favorable, unfavorable, but there is a whole lot of things that happen downstream. And it is also your responsibility to think about it and to consider all these possible scenarios that could happen. So, to close the lecture, it's really hard to avoid all anti-patterns. The anti-patterns will emerge in large complex teams. They will emerge at all levels, at the design, the architecture, the training, the testing, think about anti-patterns actively to make the procedures better. It's basically all about model management. It's the common theme of this entire set of lectures, ML operations. Think about ML as a large, complex process with many loops, with many feedback loops, many elements that combine together into a large, complex data management process. Think deeply and think a lot about data quality. Data is the fuel for machine learning, so you have to have robust, strong data pipelines. You have to have data provenance at hand. You have to track data quality. You have to monitor data quality, and so on and so forth. A lot of anti-patterns is directly connected to data, and these are anti-patterns that software engineers will not know, right? Because software engineers are very familiar with anti-patterns from software engineering, and those usually touch upon architecture, code, and testing, but they are not so familiar with anti-patterns that relate directly to data. So document data lineage, document every single transformation that happens, build audit trails, build pipelines, build documentations, use ensembles, because the ensembles tend to be more robust. If you have several different models, then they can compensate each other, and when one starts failing, maybe the other one can take over in the case of errors, in the case of concept drift, or in the case of data drift. And also think about the role humans play in all MLOps process, because this human in the loop with operational capability to intervene, to stop, to evaluate, to monitor is really important. And this human in the loop, especially when you can, this can be someone external to the data science team, someone who has slightly different perspective and different experiences and can look for different sources of errors. This can be very, very helpful. Okay, this brings us to the end of this lecture. Thank you very much. I hope you benefited from our entire section, from our entire series of lectures, and I wish you all the best luck with your future machine learning endeavors. Thank you once again.